I'm Tim Ventura from AmericanAntiGravity.com, and this is a compilation of the footage for our Vortex thruster experiments from 2002 to 2005. One of American Anti-Gravity's most popular projects was the Vortex thruster, but it was also one of our least understood. This video is an overview of our Vortex thruster experiments between 2003 and 2005, as well as an introduction to the concept of creating an artificial tornado to generate lift. This is a project that nearly anyone can build, but attempting to build a prototype suitable for testing may require a substantial financial investment. The Vortex thruster relies on a new form of aerodynamic propulsion, not on any kind of anti-gravity effect. The vortex that we describe is generated by a high-speed rotating centrifugal fan and utilizes very conventional aerodynamic principles to generate lift. What makes it unique are the application of those principles in a novel manner, not the principles themselves. The Vortex thruster itself was the brainchild of Russian immigrant scientist Dr. Mikhail Goldstick, working as a specialist in high-speed rotating flows in gas and liquid at the University of Houston's Department of Mechanical Engineering. Dr. Goldstick passed away in 1997, after which this research project was shut down. What makes the device unique is that the incoming and outgoing air both use the same orifice to enter and exit. They're kept separate by flow separation in a high-speed rotating airflow. In other words, you can mount this in the top of a wing and create lift over the wing surface without any airflow exiting underneath. Goldstick claimed that the primary application for this device was to replace the helicopter with a new type of VTOL aircraft, up to 20 times more efficient than today's best technology. Additionally, this aircraft would use internally ducted centrifugal fans, giving it an advantage in crowded urban airspace. In other words, in addition to more power, it gets rid of the dangerously delicate rotors that today's helicopters use. American Anti-Gravity's Vortex thruster is built quite differently than Goldstick's, as we use commonly available parts to create the high-speed rotating airflow. Despite the substantial inadequacies of the components available to us, our device still produced 20 pounds of thrust and demonstrated airflow characteristics that matched Goldstick's predictions precisely. Thus, our experience validates his optimistic predictions for the device's performance. Goldstick's original design used a 10,000 plus RPM fan speed to create true flow separation between the incoming and exiting airflow, but our experiments from 2002 to present have shown that the same airflow can be generated at less than 3,000 RPM simply by adding a flow separation nozzle directly above the centrifugal fan. Thus, while our results were promising, we were not operating within the theoretical parameters required for maximum thruster efficiency. In addition to direct lift created above the fan, a great deal of additional lift is created if the Vortex thruster is mounted into a wing surface. This allows the air exiting the topside rim of the device to flow over and around the airfoil, creating essentially a blown wing surface. American Anti-Gravity has extended the vision of the Vortex thruster beyond Mikhail Goldstick's original dream by adding a carburation system to the air intake of the thruster. Our experiments indicated that a pressure differential created by the rotating flow separation generated a dynamic combustion chamber similar to that in a conventional jet engine, and that by igniting fuel within this combustion chamber, we were effectively able to create something like an afterburner for the Vortex thruster. Finally, in none of these video clips does the thruster actually move. It was secured during testing to prevent movement, and our goal was simply to demonstrate that the airflow in the device matched Goldstick's predictions. However, in several scenes, you will see the airfoil on the rim of the thruster pop off its mounting as an indicator of actual thrust being produced by the device. Again, our measurements indicated up to 20 pounds of thrust for a device operating at 3,000 RPM, utilizing approximately 1 horsepower of energy from a conventional vacuum cleaner motor. The basic working principle behind the Vortex thruster is to create a strong swirling flow to produce very low pressure above a lifting surface, which generates thrust. Swirl in the incoming airflow is achieved via an open vortex chamber, and the resulting low-pressure rarefaction is intensified by an airfoil-shaped diffuser, which ensures an attached airflow without separation. The flow enters the swirler, acquires angular momentum, and exits over the diffuser, where it reverses direction by the Coanda effect and is ejected into the ambient fluid. This airflow rotates like an artificial tornado, creating a strong low-pressure zone on the upward-facing internal top surface of the vortex chamber. Since there is higher ambient pressure on the external bottom surface of the chamber, a lift force is generated by this pressure difference. Additional rarefaction is created by the flow over the upper surface of the diffuser by its airfoil shape. Operating parameters for the vortex chamber must be determined to avoid separation over the diffuser. Such attached flow over the diffuser is possible, since the Coanda effect is much stronger in the presence of swirl and is also stronger in turbulent flows. Physically, the difference between conventional jet propulsion and the vortex thruster is that in the former, the net force generated and the power requirements are determined by the axial velocity component. In the vortex thruster, a large net force is generated primarily by the tangential velocity component, but only a relatively small axial flow rate. Hence, small power is required. Goldstick's preliminary experiments verified that thrust is in fact generated in the same direction as the exit flow. The initial conservative estimates indicate that a thruster with a 1 square meter chamber area can generate 4 tons of thrust, with 17 times less energy than a conventional jet. Now I'll speak briefly about some of the clips that you've seen here. Again, these are experiments from 2002 to 2005 and demonstrate our continuing progress in refining the airfoil shape, working on the intake flow separation nozzle, and shaping the airfoil to correctly attach the laminar airflow to the wing surface. One of the limitations in our device was that we were only using 3,000 RPM. This video clip begins to demonstrate the airflow characteristics of devices we were building in late 2003 through 2004. The paper shown, the thing being held up to the airfoil, is toilet paper. If you'll notice, it's kept an inch off this Coanda effect wing surface by the airflow that's attached to that surface. So the air truly does follow that wing down and creates a flow boundary that creates a low pressure area in front of it. Once the paper attaches to this flow, it's kept off the surface, but is also firmly attached in that airflow stream. This creates lift, similar to a conventional wing surface. We typically prefer to use smoke to test things like this, but in the case of the vortex thruster, it moves so much air that the smoke isn't visible on camera. Thus, we ended up with things that were a little bit easier to film. Toilet paper is good because if it gets sucked into the intake, it essentially shreds and comes out the exit. This is yet another experiment showing the airflow. If you'll note, even after the air leaves the airfoil itself, it maintains the same vortex shape. Again, this air is moving from an axial velocity to a tangential velocity, and then back again. If you notice the colorations in this particular device, you have white and orange. Now, your intake itself, where the paper is being held, is white on the outside rim and orange on the inside rim. There's a small gap in between the white flow separator and the beginning of the actual airfoil. This gap is where all of the actual airfoil action begins. There's a smooth, steady curve inside of that down to the actual fan chamber itself. This creates, in essence, a blown wing surface. This is something that's been experimented with in the past. One of the chief advantages of this is that unlike a conventional wing, where the air remains constant and the wing is moved through it, in this case, the air is moved and the wing remains constant and isn't moved. As you can see, this is the pressure at the intake nozzle. One of the things that we'd found was it was high enough to actually suck the paper in, oftentimes shredding it. This makes sense. A vacuum cleaner motor is built to move a large volume of air very rapidly. Notice that there isn't a lot of suction over the device until you begin to get close to that nozzle. In some ways, this was a limitation of the fan speed that we used. Goldstick felt that it would create literally an artificial tornado that may reach several feet up from the device. We had several limitations working with our off-the-shelf equipment. We shaped the foam by hand, literally using X-Acto knives and sandpaper. And one of the limitations was that the laminar flow didn't attach correctly to the airfoil a lot of the time. Thus, in many of these clips, you'll see the paper being held doesn't always stay within the airflow, but if it's held in the sweet spot, it often does. As you've seen, the airfoil just popped off the front of the device. This is yet another indicator of the thrust generated on the airfoil by the Vortex throw. One of the things that we'd found was it generates, again, around 20 pounds of thrust altogether. We had secured it using epoxy, duct tape, and different types of glue to ensure that it wouldn't come off. But in some instances, the thrust was simply too great for any glue to hold it, and it would just detach itself spontaneously. Here's a piece of paper being held in front of the fan with nothing attached, showing that there is a rapidly moving vortex of air, whether or not the airfoil is present. This paper is literally spinning around in circles. This is the Vortex Thruster 2. This device was not highly successful. The hope had been to build a device with a transparent center to better demonstrate airflow in the chamber. The chamber in this case is not very deep, probably not deep enough. The centrifugal fan is a very low-profile metal one. Now we return to our more conventional design. Again, even being secured, you can see the device begin to move when it's turned on. Again, we're injecting baby powder into the Vortex thruster because it's one of the few things thick enough to actually show airfoil. If you look at the top of the wing surface, you can see the powder coming out from the chamber, sticking to the airfoil as it flows out and behind. Again, this is an indicator that even with minimal airflow, you still get considerable thrust. Notice now how the airfoil is off-center from the flow separator. This means that the device will have more flow occurring on the top, exiting the device, than it will on the bottom. This was one of the many flaws in our construction techniques. You can see me repositioning it there. This is the beginning of our carburation tests. We're quite literally using the old hairspray and lighter trick, which I do not recommend to try at home. This is very dangerous. We'd found that it was very difficult to ignite the fuel, in this case a standard aerosol propellant, because of so much air moving in front of it. So there are many tests where you see me clicking the lighter with no result. Now the flames in this case are shaped by the incoming swirling airflow, which begins to rotate before it ever gets into the thruster. Again, this is Goldstick's artificial tornado. In some instances, I'm spraying into the top dead center of the device to show air going in. In other cases, I will inject the flame over the airfoil itself. Two different purposes. One is to increase engine speed and test our carburation idea, and while I had the flame handy, the other was to show yet another example of the airflow on the outside, over the wing surface. This particular vortex thruster was literally destroyed by using flames with it. That's partly because the engine itself overheated, and partly because the flames, once they enter the combustion chamber, become intensified in terms of heat. This was one of the beginning indicators that there was enough of a pressure differential to create something like a dynamic combustion chamber. As you'll see in a minute, this device will actually be destroyed on camera by simply too much heat for it to dissipate. Now, the purpose of the blue backdrop, which you can see moving to the right, wasn't really artistic in this case. It was to provide a good dark surface as an offset for the light-colored flame and smoke, hopefully giving them more definition. Unfortunately, because the device was moving, and because the flame is very difficult to keep steady, we kept changing camera angles and ended up losing a good part of that backdrop. It's just shifted too far out of frame. As you can see here, the flame itself, again, being injected sideways into the device, is constrained and moved into that intake by the rotating airflow. This is the point where the engine itself breaks down. The pressure differential makes combustion happen more rapidly. What we'd found was, despite the average temperature of the flame, that temperature was greatly increased as it got into the combustion chamber. And there we go. That's the breakdown of the electric motor. This device literally caught fire internally. We had to set it outside and let it sit for about an hour and a half as it continued to smoke. This was the point where I had really started considering using a metal device through and through, rather than the mostly plastic vortex thrusters we've been experimenting with up until then. This is mid-2004 that we took this. The device that you're looking at took approximately 6 hours to construct and had already undergone several hours of testing. So by the time this happened, it wasn't a complete loss, but it was a waste of time, and the airfoil in this case had worked very well. This is the device and the airfoil that generated 20 pounds of thrust. As you can see, it's mounted at an angle to show airfoil. There are lead weights in the base to keep it steady. And we've removed the air injection system from the back. In fact, the second column of smoke that you can see to your left is where that would attach. Now, like any combustion chamber, compression within the chamber makes chemical reactions happen more rapidly and greatly increases the temperature as well. This is the same in any engine, in any vehicle, at least as far as I'm aware. So the fact that this caught fire and burned internally because of what was a relatively short exposure to that flame led us to wonder if perhaps this couldn't lead us to some new type of combustion chamber, as it illustrated that there was enough pressure in there to greatly increase the internal temperature. This led us to the metal device shown here. This device has a much larger inlet flow separator, and it has no airfoil. So this device here produced very little thrust because there was no Coulomb effect, no laminar airflow coming out of it. The stainless steel vortex thruster was built with one purpose in mind: to provide a completely metal enclosure, including a metal fan blade, to take that incoming flame and see how much that would affect the device itself and its operation. What we'd found was, by injecting flame into the center, the resulting combustion boosted the RPM about 30 to 50%. Notice that the majority of combustion happens before the flame even reaches the combustion chamber. This was a real indicator that if set up with a true carburation unit, which we experimented with later, we would be able to see substantial increase in performance for this device, creating, in essence, an afterburner. Obviously, this is a messy process for testing, and this brings us almost to the end of our footage. We plan on undertaking more testing with the stainless steel device in the future, but due to the nature of filming with this, it is difficult to get good quality footage. Here is a test with smoke. Again, you can see the smoke literally disappears. Thanks again for watching our compilation footage for the Vortex thruster from American Anti-Gravity.